this seems pretty simple, but what it actually does is it helps us to implement pretty fast streaming services, such as it helps us to implement real time applications, like suppose pizza ordering and fraud detection, gaming, and like in the morning, like now I have just in the morning I've attended Kafka sessions, and in that they were telling something about fraud detection of currency, and they are actually using Kafka for that, and Kafka and machine learning for that. So it's pretty, and also it's fault tolerant because it's a distributed system. So uh, bringing it down is not that easy because as it is distributed, the whole focus is not only on one single server, so that makes it very strong. And also, it's you can see that used for decoupling data stream. That means uh, the producers and consumers are unaware of each other. Like what is the writing what and what is reading what, it's unaware. Like both of them are unaware of each other. So uh, as I said that I will be discussing some of the parts which I've studied. So very first one is topics and partitions. So when I first studied topics, I was a bit confused. So I have understood it with an analogy terms. So see, what is topics? Stream of data. So we put it very simply, it's stream of data. And these topics are divided into partitions. Now, if we want to understand it a bit more clearly, we can take example of a book, history book. For example, we are studying history, and the topic or a chapter is Cold War. Now, in that Cold War, we have partitions. Suppose fall of the Berlin War, or split of USSR in 1991. These are two topics. For example, these are two topics. These two topics, you can consider them as paragraphs. You can consider these paragraphs as partitions. These paragraphs will contain lines, and these partitions will have offsets like lines. You can see that these are lines. So suppose these are topics, and they are three partitions. You can consider these partitions as paragraphs. So partition 0 will have some number of lines. Partition 0 will have six number of lines. Partition 1 has two number of lines. Partition 2 has partition 1 has three number of lines. Partition 2 has four number of lines. So what we can see that these are serially ordered always. They won't be like haphazardly, like after 0 comes 3 and after 3 comes 1 and after 1 comes something else. Like they will be ordered uh, in ascending order. They will be in ascending order, and they will have an offset which you can consider as an ID. So partition 0, like the data that will be storing is that we will be storing in partitions. They will have an ID. So in topic, we have partition. Partitions will be subdivided, and those subdivided parts will have offsets, ID. So if you take this, like, and yes, one more thing, topics will have names. As I said that we are studying Cold War, for example, they will have a name. So this, take this some simple example. It's a very if you want to place pizza, and in between comes the Kafka architecture, and then we want to receive the orders. Now, what I have generally seen, like where I live, there are four shops for Domino's, and whenever I place the order, seen that I have never seen that an order go into same shop. Most of the time, whenever I place an order, it will either go to A, it will sometimes go to A, sometimes it will go to C, sometimes to B, sometimes to D. It will never go to same place. So I tried to dig up on it a bit, and I found out that these pizza joints, Domino's for example, are actually using Kafka. So that's what makes it very fast. Like whenever we place an order, just like after 2 or 3 seconds, they confirm that this shop will be uh, taking our order, and they will be delivering this and that, all those things. So guaranteed orders is guaranteed only in partition. Like if you see these numbers are in order in only one partition, but it's not guaranteed that order will be across partition. Only in single partition order will be possible. Otherwise, it won't. Like here, you can see that 000, but it's not always the case. Therefore, in partition, the in partition order is guaranteed. Across partition, it is not guaranteed. And data is kept only for a limited amount of time. You can keep it for any amount of time you like, but it will incur cost, and we want to reduce it. And since it is for data process, right? So once the data is processed by the other side, there's no need to keep the data, so you can remove it. So therefore, it is best practice to keep it for a limited amount of time. And one more thing, once you have written data into a topic, you cannot edit that. You can send a new one, but you cannot edit that. So moving on to next topic, brokers. What are brokers? So you can consider brokers as server, and these brokers actually hold the topics, and each broker has an ID. That's how you will identify them. And group of brokers are called clusters. I will be showing an example that will make it more clear. And the partitions will be placed according to the logic that Kafka is having inside them. Like I will explain that. And one best thing is that if you connect to one broker, you will access all brokers, and you can get the topics and partitions that they contain. Yeah, look at this picture. For example, there are three brokers, okay, and they have an ID 401, 402, and 403, and we are having two topics, topic A and topic B. Topic A has three partitions, topic B has two partitions. So you can see that this one has topic A partition 0, then topic A partition 1, topic A partition 2. There is no fixed rule. There is no fixed rule, as I said before, that there is no fixed rule that where in which broker a topic with a particular partition will fall. There is no specific rule, but there can be. Like I will discuss that later. And and as you can see, that topic B partition 1, topic B partition 0. This one can also could have came here, but I have put it here. Okay, it can also come here. This one can also go there. That thing is actually controlled by the Kafka architecture. We don't have to worry about this, that which topic will go where. It is decided by Kafka itself. Okay. Replication factors. Now this is very important. So what is replication factor? Replication factor is number of times you want to keep copy of something. Here if you see the definition, number n, which tells Kafka to hold n copies of topic x partition y. Why, what it means, I will show that in the picture. Like we are discussing it with n is equal to 1. Here you can see that a particular topic is only repeated for one time. You cannot see any other place where topic A partition 0 is present. Okay. So till now I was discussing with n is equal to 1. But usually, like in industry standard, it is between 2 and 3. It is said 3 is the gold standard because suppose we are one is down and another one is used for maintenance. There will be one which will have our information. So suppose take this example. Here factor example n is equal to 2. Topic A partition 0 is also available in another broker topic A partition 0, and topic A partition 1 is also available in broker 403. Now what happens? Suppose this server falls down and this server falls down. This will still be there, right? So what we can see, our topic and partitions are there. We don't have to worry about this. Suppose this one falls down, these two are there. This one falls down, this one is there. Okay, and you connect one, you get all. Simple. Okay, now yeah, replication factor and broker. Yes, one more. This one is important. See, what happens is you are putting a, a a message in a topic with a partition, with some partition. So suppose there are three. As you can see, there are three brokers, three servers. At a time, there will be one leader for a partition. Okay, one leader for a partition, and another will be followers. So suppose if you see here, topic A partition 0, this becomes leader and this becomes follower. So whatever request to read or write goes here for the leader. Once if this goes down, then the producers and consumers that I will discuss later will make this one as leader. Okay, for some time, and then again it will shift back. Same you can see here also. For this one, topic a partition one, not partition zero. Partition one, it has made this one leader and this one as an follower. And these one are called ISR, multiple ISR. This is called in sync replica. And each partition has one leader and multiple ISR in sync replica. Okay. Okay. Next is producers. Now, what are producers? To put it simply, producer are something which are writing into the topic. Okay. Sources where we are actually getting the data and we are putting the data into our Kafka clusters, and those Kafka clusters are containing it inside there, into the brokers. Okay, so as it, and they know everything in advance, like which broker is active, which broker is down, and they are really very smart. Like they are programmed that way. So if even if one of them fails, they can recover automatically. Like they are very good. They're well programmed. They're programmed that way. And okay, I will discuss this into next diagram. I think I have one. Okay, fine. Okay, fine. So see, these 3 points, I will show you via this diagram. If you intend to send a message with a key, messages of that will always go into same partition. Um, if suppose topic, there is a thing called topic, but I want to use a particular key. For example, earlier I have shown you an picture for pizza ordering, right? So suppose I am making a key shop A. So that thing will, if I use a key shop A, that will always go to partition 0, 0, 1, like some like this. If and not only I'm not saying that it will go to broker 111 or something like that, but once if it selects a partition, it will go there only, and then it will record its offsets and all. Okay, but in case you try to add extra partition, I think, yeah, extra partition, that time it will change the partition. If you add another one, then it will change the partition. It will move to 3 or 4 or 5, something like that. Okay, but until unless though that is changed, it will keep on storing that in same partition. So if you have key, it will go to single partition. If you don't have key, it will store it in round robin way. Like first it will put it there, then it will put it there, then it will put it there, and then again it will move back to here. Okay, it will follow round robin way. Yeah, key set to null, data is sent in round robin. Okay, so this one is done, and yeah, acknowledgement for producer. Now what is actually happening? Uh, we have TCP and UDP, right? Those two protocols that we have studied. TCP is like it gets the acknowledgement, but UDP doesn't get the acknowledgement. What actually happens? Suppose I have sent a request to store it in the broker. Like suppose this one has sent a request to broker 111 that please take this data and store it into your topic. Now what it does that it if it only sends the request and then it forgets it, then how we will know that it has written that data into the topic for sure? We don't know, right? So there's high chance that our data goes missing. There's high chance that it will happen. But as I've discussed earlier in replication that there is sometimes there is a leader and then there are followers, the replicas. So what will happen? You put the data and the leader will confirm. Yeah, x is equal to 1. The leader will confirm. Other followers won't confirm, but leader will confirm. So what will happen? That we will be sure that the data that we have sent to broker, that will stay in the that is in our Kafka. Okay, but we are not sure that the followers are having it or not. But if x is equal to all, these are configuration settings. Okay, x is equal to all, then what will happen? We will be totally confirmed that apart from leaders, other followers are also having our data. That our data list is 0, and if suppose it fails, it will try again. Okay, you have that thing like after 2.3 or 2.4. Like I'm not remembering the number exactly. After version 2.3, 2.4, it has started. So yeah, so this is for producer, and similarly, consumers are for sorry. consumers are for reading the data from the topic, because we just not only want to put the data into somewhere, right? We also have to consume it. Otherwise, it's simply you can say kind of a database, but we have to read it also from there. So it knows which broker to read from, exactly like producer. Producer also knows that which broker I have to write to. Consumer also knows which broker I have to read from. Okay, and like producer also, this one is also very intelligent. Like it knows which one has failed, and if somebody has failed, it will recover automatically, and it will of course read in order. Otherwise, it doesn't make sense. Like it will not read four after five. Okay, it will read in order, zero, one, two, three, as it is. So consumer can read from multiple partitions, read them parallelly. Kind of. See what this line actually means. Sometimes there are group of consumers. Okay, so they try to read uh, this data from Kafka clusters at the same time, but not exactly at the same time. Sometimes it will fetch four records from one broker. Then after some time, it will fetch two records from another broker, like that. But it's so fast that it is that they are saying that it's reading them in parallel. Actually, it's not. Technically, it's not possible, but you can say that it's reading them in parallel. Okay. And if you have more consumers than partitions, then some consumers will be inactive. Okay, what this line means? Suppose there are four brokers. Okay, let me show you. Okay, images. Okay, suppose there are four brokers, and there is six consumers. And for a data for a group, like in that group, there are six consumers, and there are only four brokers. So if the four consumers are reading from the four brokers, those two will be silent. They won't do anything because they know that it's already sufficient. Why to waste energy? So they will stay as silent. So they will be staying active. Oh, okay. So okay, this one is clear. What consumer offset means? Consumer offsets are actually kind of record where which shows which exact uh, data is read from the Kafka cluster. What actually it means is, suppose we have started reading the data from offset 4 to 56. Okay, we are we are reading the data. After 459, server crashes. For example, server crashes. Now, all these things like till which offset have been read is stored in another Kafka topic, which is named as underscore underscore consumer underscore offsets. This one. Okay, it stores it there. So once it comes back again, the consumer will know that till which when we have read the data from data till when we have read the data, and that's 459. Then it will again continue from 460. Once it does that, it will commit. It will read in this way. It was I have discussed earlier, just in this earlier slide, that um, it will read in order within each partition. Okay, so therefore it will wait. It will see that until which offset I have read. If it fails, after failing it recovers back, it will check which one I have read, and from there it will carry on. Okay, so this is consumer offset. Delivery semantics. Now, what is delivery semantics? So there are three delivery semantics. One is at most one, at least one, and exactly one. What in this one actually does, as soon as the consumer contacts the Kafka cluster and reads the data, it commits the offset. Like for example, as soon as I read 459, I haven't processed it yet. As soon as I read 459, the data in offset 459, I commit that okay, I have read. So what happens before processing, in case the dependent service, which is based on our consumer, fails, it will again it will not go back to 459 and fetch the data. So what we are actually having, we are having a loss. It's risky. So this is at most one. Okay, at least one. This one says it is usually preferred. What it actually does is only after the message is processed. Like if we have come to 470, we read the data, we have processed it, done whatever we wanted to, put it into a dashboard or in the application or in database, whatever we did. After we do that, we commit it. Then what happens that we are totally safe. And but in that case, suppose before committing our application failed, then it will again come back and read from 460. Okay, it seems I have by mistake missed some number, but anyway, I think you guys are getting the point. Just like suppose it comes back to 469. Okay, till 469 is there. I have processed 478, but due to some reason, server failed and 470 was not committed. It will reread the data again from 470. For that, what you have to do, for that it is necessary that our endpoint, the consumer endpoint, should be idempotent. Now, what it actually means in mathematics, we have studied idempotent operations, right? 1 into 1 is equal to 1, 5 into 1 is equal to 5. So it has to be idempotent. Like if you are processing the data and whatever you are doing it with, it should not affect the one which we have already processed. Suppose we have processed the data and put it into our database. If we reprocess that data and put that in our database, it should not affect it again. Hence, idempotent. Exactly once. Okay, I am actually a bit confused a bit on this exactly once Kafka to Kafka flow, and it says idempotent consumer is needed. But I think it's something like this. Um, okay, I'm skipping this because I'm not a bit sure about this exactly once. Like I have just read about this like last night only, or this exactly once. Anyway, but I think these two are clear, right? Any questions on this? Am I audible? Hello.
Yeah, we can hear
So
you.
okay, fine. So at most once and at least once. Exactly once. I think it's just I have studied like it's for Kafka to Kafka flows because we can integrate Kafka to Kafka also, right? So for that case, this exactly once is there for that delivery semantics. Okay, so next Zookeeper. So with Zookeeper, you can think Zookeeper as a guard, which is keeping everything, which is trying to control everything. So the Kafka clusters which is actually ran, that is controlled by Zookeeper. Without Zookeeper, Kafka clusters won't run. Okay, but we don't have to worry about Zookeeper, but we should know that Zookeeper is a very important aspect in Kafka. So for leader selection, it is very important. Like if something is failing, something broke down, it will manage and reselect the leader. And also it operates with odd number. Like if it starts with 3, 5, 7, like that it goes. And as in this also you can see that Zookeeper has a leader, rest are followers. And Zookeeper does not store consumer offsets after version 0.1. Like I have discussed consumer offsets here, right? This one, the committing part. So it's not storing Zookeeper. I mean, it's not storing consumer offsets after version 0.1. So you can see this kind of a graph. You can see these are brokers, broker one, broker two, three, four, five, and six, and these are zookeepers, and this becomes a leader. Okay, and if you see it, you can see that this is a graph, and hence if you connect to one broker, you can get all brokers. If you connect to B4, you can get B3, right? And you can also get B1. You can also get B5, or you connect to B6, you can get B2. What is this? This is a graph. I'm not remembering the exact mathematical term for this, but this is a well-connected graph. I think this is a well-connected graph. So this is zookeeper example. This is a kind of zookeeper. This is a zookeeper example, and that's all. Thank you. Any questions for this? Thank you. Thank you.
Thank you, Kushal. Uh, Kushal, a very good presentation actually. So, so you have basically worked on. So we will be basically working on a demo project, or we are basically going to go through the current Kafka implementation after this, correct? And then we are going to present it in the next meeting.